Hi, this tutorial is on assurance of distributed algorithms and systems, runtime checking of safety and liveness. My name is Annie Liu. This is joint work with Scott Stoller at Stony Brook University. Where is Stony Brook University? This is New York City, Manhattan. Stony Brook is 55 miles east of Manhattan. First, many thanks. First, to fabulous PhD students who did great works. Bolin on this algo compiler, runtime system, Sakshan Trend, formal verification of pixels, Jonathan, Michael, and Tom, all on automatic incrementalization. Also, wonderful colleagues with insightful discussions on many intriguing algorithms in distributed systems and blockchain worlds, and on languages and optimizations, and to support of NSF and ONR grants. This is the outline. There are 4 parts for this tutorial. First, an introduction to distributed systems and algorithms and their safety and liveness properties, with examples: distributed mutual exclusion, distributed consensus, very classical problems. Second, a method and language for expressing distributed algorithms. The language is called distalgo. It allows you to write high-level, precise, and executable specifications. Then, we introduce a framework for runtime checking of safety and liveness, including formal specification of the properties and automatic state collection and checking. Finally, we show experiments and give a demo. You only need Python to run this algo, which is an extension of Python and is open source. We'll give complete executable specifications with complete examples, so you can run yourself. So you can ask questions anytime if you happen to see this tutorial even before the real tutorial, and during the tutorial and afterwards. Send me email or type in the chat during the tutorial. So now the first part. Distributed systems. A distributed system is a set of processes, fancy names like agents, parties, players, entities, or live objects. Each process has private memory, no shared memory. The private memory is not accessible by anybody else except the process itself. The processes communicate by sending messages, message passing, but with delays. Whether you have or have not experience with distributed systems, they are actually everywhere. You can think about yourself as one of the distributed processes, and you communicate with the others by sending emails. Okay. The most distinguished feature of distributed systems is failures. There are many of them and many kinds. I grouped them into these 4 big classes, but the first 2 really captures the essence. Process failure, so process can crash and later recover, or it may be too slow, or you could even tell whether it's crashed and recovered or it's too slow. And link failure, that's communication channels. Link can drop messages, delay messages, reorder them, duplicate messages. And both of them really fundamentally give you the asynchrony, and they are actually can be modeled with each other. There was one big class of failures where process and links can do worse than just crash or drop messages. They can behave arbitrarily, misbehave, or attack. And even further, there's a class called the SIBO attack, where processes, so even in Byzantine failure, you still have identity of the process. But in SIBO attack, process identities can be pseudonyms, that's false names. So let's just look at all that kinds of applications. There are many classifications and descriptions. I group them into 3 classes. The first is real-world distribution. Okay, in real world, you really have separate data storages and remote information sources. okay? And you have separate computing units and processing entities. Examples are everywhere: corporate management, air traffic control, mobile applications and games, and general collaborative or competitive activities like auction or election, okay? And second class is the problem doesn't have to be distributed, but for better quality of life. So to enhance reliability, you might replicate your machines, right? Have separate backups. To increase performance and scalability, you might do parallel computation. Examples are cloud services, high performance computing, replicated state machines. And finally, it's just way of thinking, ease of modeling, conceptual separation of data and conceptual separation of processing. Examples are modular problem solving, including OO programming, object-oriented programming. So this is really the age of distributed computing, right? From decades ago, telecom industry is really already doing distributed computing. Of course, with information on the web, search engines, social networks, cloud computing, mobile computing, and currently pandemic has made the lives drastically more distributed. We can see that distributed systems are just increasingly important and challenging. And at the core of all of this are distributed algorithms. Okay, so example, distributed computing problems that needs distributed algorithms. Distributed mutual exclusion, we'll see, leader election, distributed consensus, atomic commit, replication, clock synchronization, distributed file systems, distributed database, just name it, network routing, broadcast. Okay, so two concrete examples. First, distributed mutual exclusion. Okay, the problem is you have multiple processes. They need to access a shared resource like a printer, and they need to access it mutually exclusively in what is called a critical session. That is, no two processes are in the critical session at the same time. Okay, so you don't have two processes trying to print at the same time, you produce garbled print. So how do these processes communicate? Can process or links fail and you still guarantee mutual exclusion? What exactly are the correctness properties? And what are efficiency measures? Okay. Second problem, distributed consensus. Here, multiple processes need to agree on a value or a sequence of values. These are essential for replicated services. If you have distributed services and you want to be tolerating failures, and you have to replicate, but the replicate machines or replicas, they have to agree on what's the state of a system, what's the sequence of transactions it has processed, right? So they know, okay, customer has paid, but has not been delivered to the goods. Okay, this is actually an easier problem than distributed mutual exclusion. Same basic questions as before, and even more can be asked. How can processes or communications fail? Okay, actually for mutex, generally processes and communications cannot fail and still guarantee mutex. Okay, and here also, is it possible this problem is not solvable at all? Okay, indeed, there's a famous impossibility result. We'll see. So the exact properties, as we're trying to talk, are grouped into two big classes called the safety and liveness. Informally, safety means some bad things will not happen. And liveness property ensures that some good things will happen. Okay, you really need both. Because you have a safety, that means some bad things will not happen. But if nothing happens, it satisfies some bad things will not happen. It's safe, but nothing gets done. Liveness property ensures some good things will happen, okay? But it doesn't exclude the possibility some bad things happen, so you really need both, okay? So let's see example properties for distributed mutual exclusion and distributed consensus. So the red ones are safety properties examples. So for mutex, the key safety property is at most one process is in critical session at a time. Okay, but again, if nobody's in critical session, it's safe. So to ensure that, we have to say some requests are eventually served. Okay, and this might not be strong enough. If somebody's requesting and that person's request is always served and mine is never served, that doesn't sound like a good thing to me. So stronger ones can say all requests are eventually served. Okay, and you can say actually with Lampert's distributed mutual exclusion, you can say all requests are served in the order of logical clock values. Okay, in fact, you can see here actually it's a little vague. Is this a safety property or aliveness property? If you want to emphasize all requests are eventually served, and that's aliveness property. But if you want to emphasize they were not served out of order from the logical clock values, then it's a safety property. So in practice, usually when you write some properties, it actually has both aspects. Okay. For distributed consensus, the number one safety property is non-faulty processes decide on the same value or sequence of values. This is called agreement property. And the second safety property that's most famous is called validity. They do agree on some value or sequence of values, but the values they decided on must be among allowed values. So they don't just vacuously agree on some trivial thing, set ahead even. Okay, and the liveness property is called a termination, says that non-faulty processes eventually decide. Okay, these are just some examples, but those are the most famous ones for consensus. This is called agreement, this is called validity, and this is called non-termination. I'm sorry, termination. And for mutual exclusion, right, this is called a mutual exclusion. This is usually called deadlock freedom, okay? And this can be called a fairness, okay? So indeed, there is a non-termination there. There's a most famous result called the FLP result, impossibility of consensus in asynchronous distributed system, which is practical distributed systems. Even with only one process that is subject to crash failure. Okay, theoretically, you cannot guarantee termination and reach consensus. Okay, so checking safety and liveness. So checking safety and liveness properties of distributed systems involves checking properties about multiple processes, the set of processes in the system. It's a global property, okay? So it requires you to know the state of all those processes you were talking about, okay? But remember, the key aspect of distributed processes is that the state of a process is private to itself. It cannot be accessed directly by any other process, okay? The only way other people can know anything about it, remember, is by sending messages. So the best anyone can do is to observe a process from external, okay? So intercept messages sent and received by the process, and then determine the state based on those and check the desired properties. And you can only check conservatively or approximately and with a delay. Okay, this is in practice with those asynchrony. Okay, so we have one term called a checker. That's essential for this talk. It's a process that does the interception of messages, does the observation and deciding of properties. Okay, indeed, a checker needs to see the intercepted messages. All right, so that basically finished the introduction to distributed systems and safety and liveness properties and checking. Okay, it's very short, but it has all the key aspects. Okay, that's part one. Now move on to part two. A method and language for expressing distributed algorithms. Okay, we'll start to give complete executable specifications. We use one running example I made it up, called the polling problem. It has a polar process and a set of poly processes. Okay, so what the polar process does, it sends a question to a set of poly processes, waits to receive replies from all of the poly processes, and then sends the outcome message to all of the poly processes. Okay, and for a set of poly processes, each of them waits to receive the outcome at the end. While waiting, when it receives the question, it sends an answer, a reply. Okay, that's the idea. See, send message, wait, and send, and wait to receive. When receiving, to sending. So you see, this is the communication between these processes. Okay, and to make it a really complete example, I have to be concrete. So here we say the question to send is, did you attend RV? Yes or no? Okay, so the polar will send this question. And after receiving replies from all polys, it will print out those who replied yes, so we can see what happens just for ourselves to see. And then it will send the outcome to all polys, and the particular outcome is the number of polys who replied yes. Okay, and for the poly, when it receives a question, the replies, it is selected randomly from Y and N. Okay, yes or no. And after receiving the outcome from the polar, it will print out the outcome you receive. Okay, and for all processes, polar and polys, okay, they must be properly created and set up to communicate as desired. Okay, these are real distributed processes, can run on different machines, and they have to communicate. And in particular, in this case, the polar needs to know the set of polys. Okay, so how do we write this, right? This is almost like pseudocode, but I want to write precisely, and you can actually just run it. Okay. Oh, actually, I forgot to say, maybe you think, oh, that's so trivial. Send a question, wait for reply, send outcome. And these people here just wait for a question and send a reply. But I want to say this polling problem that is only seemingly simple. Okay, by the way, there's some small variations. You can wait to receive replies. The polar can wait to receive replies from a subset of polys, like majority, or some percentage. It doesn't have to wait for replies from all of them, especially when you have failures. And you can send outcomes to only the process that replied, not everybody. And you can wait until some timeout. Okay, this problem is actually both essential and non-trivial. Okay, it's essential because all distributed processes, or you as a person, as a process, are always working with a set of other processes. Okay, that's the core of algorithms for fundamental problems, including distributed mutual exclusion, atomic commit, consensus, you just name it. Okay, and it's like everyday life. You can think about the instructor giving assignments to students, wait for all submissions before posting the solutions. A company serving customers, or a campaign manager polling voters. Okay, and it's non-trivial because even without process crashing or message delays or losses, just perfect communication, no delays even, no crashing. Okay, how do you know when you receive some message, it is a reply to your particular question? You might be asking a lot of questions, right? And some people might just send you something that look like a reply, send a yes, no. You can say, I can put the question, subject and titles, but somebody might just have sent you a message that looks like a reply. Okay, so indeed, to really be sure that was the reply to your question, you have to put in some kind of IDs. Okay, and then how do you know the replies have been received from all polys? You can say, oh, I'll check, I'll count how many polys I sent this, how many replies I received. But remember, messages can even be duplicated. Okay, you have to be really careful. And this is when you have perfect, no failure of any kinds. Now, if you have process crashes, message losses, out of orders, right? And not to mention simple attacks, you even need the security protocols. Okay, so let's see, how do we say those? Okay, so essentially those are algorithms. So if you want to program them or specify them, okay, just quickly, programming language community has made significant advancements, and think about all these famous languages allow you to do all these fundamental things, okay? But that's mostly sequential and centralized, okay? So it's not concurrent, not distributed. For concurrent programming, it happened to be, by the way, the key idea underlying that is threads, right? You all should all know that. Multiple threads, they have access to share the data. In Java, it's actually popularizes threads as concurrent objects. The concurrent programming model in Java really just have threads, you can start them and access shared memory to communicate. And this has been adopted by other languages like Python and C#. Okay, really they make concurrent programming into something everybody can do. For distributed programming, it's actually a lot worse. You have to use low-level or complex messaging libraries, or with restricted programming model, like low-level socket libraries, C, Java, all major languages have this library, or MPI, again, for high-performance computing, message passing interface, or RPC, remote procedural calls, or Java remote method invocation, and processes, built-in processes in Erlang, or other more theoretical study languages. But when you really study distributed algorithms, not building real applications, but programming, people use pseudocode English. They're high level, but imprecise and not executable. Or they use formal specification languages that's precise, but they usually very low level, okay? They're much little progress. But it's not people haven't studied programming languages early, okay? It's a beautiful language, okay, even functional. And the Argus by Liskov, people know Liskov is famous for inventing abstract data types, or programming, or Liskov substitution principle for modular programming, or the clue language. But that's only the easy part of her work. And the harder part of her work is actually distributed computing, extending clue to language called Argus, and the famous algorithms to do consensus called the view stamp replication and the PBFT, okay? Emerald by Andrew Black, etc., even allows process migration. Links by Michael Scott, who wrote the beautiful programming language textbooks, even though officially he's not a programming language researcher, and so on. And there are even more declarative languages based on data log, etc., and other special languages. And of course, we talk about the libraries in standard languages. Okay, real programming. And formal specification languages with Lamport's TLA and Pascal with the whole toolbox to do specification checking and proving. And Pramila, Alloy, Daphne, lots of these formal specification languages, and IO Automata by Nancy Lynch Group, CSP by Tony Hoare, CCS by Robin Melner, and all kinds of language to even specification languages to even specify security protocols. Okay. And of course, as I said, in algorithm studies, people use pseudocode in all kinds of textbooks, okay? But good algorithm designers, they try to write really carefully and beautifully, okay? So if we really want to have a language for expressing distributed algorithm, we really want them to combine the best of all three: pseudocode languages, which gives you a high-level flow of control like the algorithm; specification languages, which are languages with precise semantics, you know exactly what happened, no ambiguity; and programming languages is also precise and it's executable. Okay, although some of them do not have formal semantics. Indeed, by the way, you should do all three, even for centralized sequential algorithms, solving any hard problem, not just distributed algorithms. And this algo is designed exactly to achieve this, to support all three. It's a powerful language for distributed programming. Okay, so let's look at the polling problem again. This is the same slides you've seen before. The poller sends question to police, wait to receive replies from all, sends outcome to all, and these are all the details. And the poly, each of the poly waits to receive the outcome, but while waiting, when it receives question, it sends reply, and here are some other details, and then all of them have to be set up. So how does this algo do all of this? Okay, and here's the complete program. called a polling.da. Okay, this is a completed file. You can just run with Python after including the disalgo module. So you have a class P. That's a process class. That's the polar class. Okay, and when it's set up, you should know the set of poly processes. We call those responders. So set of responders. Okay, pass means you do nothing in Python. And then you have a run method. That's what the body of the polar will do for this polling. Okay, so it takes a value from logical clocks. This is the current logic time into T. So it sends a question, and whatever the question it is with this time to the set of responders, the polys. Okay, and the question here is just normal function, returns the string. Did you attend RV, yes or no? Okay, so that's the sending. Afterwards, it wait to receive things that satisfy this condition. So wait for each R in set of responders. You have received the some reply, okay? And that reply has the same T. This underscore means the same T, okay? I don't care the middle components, that's this underscore, from each of these responders. So then this R means this R is the underscore. Okay, this is probably the most complicated sentence because you see you have await, each, and some. That's like for all exist two quantifications, even alternating quantifications. Okay, after you receive all replies, you say, oh, I received a yes from, you find out the set of R where you have received the reply of yes, matching the same T from it. Okay, and after that, you send outcome. Okay, which is some outcome to all the responder processes. And the outcome is the count of all the responders, okay, that you have received a yes from. Okay. And the responder process, each of the poly is a process. And it doesn't take anything, so it doesn't have a setup method. It has a run method. And all it does is just wait to finally receive some outcome. That's called at all. And then just print, oh, I received outcome all. Okay, while waiting, if you receive a message, that's question, okay, with some time from some process P, and you will send a reply, okay, with this reply to this question with the same time back to P. And the reply, just a normal function, is just take this Python code, right, import a random and return a random choice from yes or no. Okay, so that's the polar and poly. And finally, set up all of them. So it's a main method does this. You configure, actually I have to use Lampert's clock. We can use logic clock. Here we use Lampert's clock. So I configure clock to be Lampert's clock. And here I actually cannot afford to lose messages. So I want a reliable channel, okay? Because I do wait for all replies for this, in this particular variation. Okay, and then I create the responders, okay? New responder class, and this means passing nothing for setup method, and created 10 of them. And for the polar, I create a new polar, I pass in the set of responders. Okay, then I start responders and start the polar. Okay, that's the complete program. You can just run. All right, more details. So here is this algo language overview. It's an extension to common object-oriented languages. We have a precise set of syntax as extension of Python. The language really just has 4 key components, okay? First, distributed processes that can send messages. Okay, all distributed languages support this most trivially. But the most interesting part are the 2 middle things, okay? Second, it has high-level control flows that handle received messages. Okay, and in particular, it has high-level queries of message histories. Okay, you can use as synchronization conditions. And finally, have high-level configurations, as you've seen some examples. Okay, so I'm just going to talk about each of these, actually one on each slide. And the red one shows the ideal syntax for such a language, and the green one shows the precise syntax in Python. Okay, first one. Distributed processes that can send messages. So there's just sort of 3 kinds of concepts. You define processes, and you set up and create these processes, and these processes can send messages. Okay, so process definition looks like that. You just say process P, and here's the body of the process. Okay, and inside the definition, you define setup method, run method, okay, and you use self to refer to the process itself. In Python syntax, you write a class and saying it's a process class, okay? And now, since the process definition includes setup and run, and then from outside, you can say, okay, I'll get some set of processes, okay, n new processes of P type at node expression. This is actually the disalgo node that can be run on any remote machine. Okay, you could actually configure with IP address and the port number, and this process will be created there. But by default, it created on your local machine. Okay, and by default, it actually runs as a separate operating system process. They will have completely separated memory address, and you could configure to run as threads. Okay, but anyway, the point is you can just create processes easily. Okay, and in Python notations like that, right? New process of type P, this is the number, this is add remote node. Oops. And then you can call the setup method, pass in the parameters for the setup method. Okay, and again, here's the Python syntax. Okay, and the setup method can be omitted. You can just, we see in the examples, you can just say when you say new prop P, you can just right there pass in the set of arguments. Okay, and finally, after you create it and set it up, you can just start the process by calling start, which actually calls the run method. Okay, and so in the process body, in all these methods inside, you can just say send a message to process expression, okay, which can be a single process or set of processes. And in Python, you write like that. To is called a keyword argument in Python. Okay, oh, these are also keyword argument. All right. So this start to be the key, okay? Control flows and receiving messages, how do you handle them? So there's one notion called a yield point. You can have a label name for it. These are the only points you handle messages. Otherwise, you behave like centralized sequential program, okay? And then you can define a set of handlers, right? Besides a setup and run method, you can define a set of handlers of this form. If you receive message, okay, from some process, add some labeled yield point, then you do the body, okay? And this is the Python syntax. You define a receive a method, receive this message from the sender at some labels, you do this, okay? And so this is called handler. It's actually asynchronous because messages are not immediately handled, only when it reaches a yield point, it gets handled, okay? And by default, if you do not say at, it will handle the all yield point, okay? And in particular, there's one special statement called await a Boolean expression, a condition, okay? And in front of every await, there's by default yield point. And if you don't put a name, it handles all messages, okay? There's a special one, you can also wait for a timeout, okay? And this is actually the general form, you can do both. And it's non-deterministic. You can wait for a bunch of conditions and timeout. So you can wait for condition 1 to be true, do a bunch of statements, or condition 2, a bunch of statements, and so on. Or timeout, do a bunch of statements, okay? So in Python, you just write using the if and put a wait in the front, okay? Elif, timeout. Okay, so by default, there is a yield point in front of every await statement. You can imagine at the high level, in fact, you do not ever need to even write any yield points, because if you're not waiting for anything, you just do your own job. You don't have to handle the messages. But if you're waiting for receiving things, then there's automatically a yield point. Okay, that's why you do not see yield point. Really, essentially in all distributed algorithms we've seen, you don't even need this, because if you write at a high level, like in textbooks, you don't. Okay, but these labels and handler here give you fine control if you want to do optimizations and scheduling. And this is a really interesting part. Okay, so you can have handlers. Oh, I should emphasize, right? These are asynchronous, meaning these guys only handle that yield point. And this is synchronous, okay? Await means I'm stuck here, okay? One of these conditions has to be true, I continue, otherwise I'm stuck here. But this algorithm allows you to do both in the most straightforward fashion, as you will do when you answer your emails. Okay, so here is the really high level part, even higher level than the synchronous and asynchronous. What can you put in the await statement? Okay, so first of all, there are just two fundamental things and two built-in variables called received and sent. Okay, these are two sequences. This is all message you ever received. This is all message you ever sent. Okay, and you can actually write saying, I received some message from some process, right? And you can really think about that. It's really just a pair. A message from process is in the sequence of received. Okay, so in Python, you can write like that notation. Okay. So with these two built-in sequences, you can actually write high-level queries. And the first one is the most classical in all set theory, right? So the set of expression values, the set of values expression, okay, satisfy these membership clauses, V1 in S expression 1, VK in expression key, and arbitrary Boolean conditions, okay? In fact, actually in this algo, you can even change the order. You don't have to put all memberships in the front, okay? And in this algo, you write a set of expression. The first one gets returned and put all these afterwards in Python notation. And you can have aggregation. And these are sum, max, min, and count, and with the same comprehension syntax. And the most amazing part in reasoning is quantifications. Okay, so you can say sum V1 in S expression 1, VK in S expression K has the property, the Boolean expression. Or you can say each V1 in S expression 1, VK in S expression 2 has the property, Boolean expression. Okay. This is exactly sum, exist, essential quantification. Each is the universal quantification. These are taken actually from ABC, which is a predecessor of Python. Okay. In particular, sum actually, besides returning true and false, it also binds the variables to a witness, so you can use it afterwards. Okay, you can actually write a kinds of a generator expression called that in Python, called any and all, but you do not have witness. That's really important for high-level programming. And finally, in all of these queries, okay, these S expressions are actually, you can write as patterns, tuple patterns, okay? When they're on left-hand side of membership, underscore matches anything, and equal V means you have to match the value of V, okay? In Python, you have to write underscore V. All right, and that's all about queries. Finally, configuration. You can configure channel types. You can say it's a FIFO channel, reliable channel, and in either or both cases, you use TCP, otherwise you use UDP and in current implementation. And you can specify how you handle messages at each yield point. You can say handle all of them or handle one of them, okay? Logic clocks, you can say configure use Lampert's clock, okay? And you can call logic times to get the logical times. Actually, we use logical clock, I think, in my code. Either one works, I think. And finally, you put all of this in the file that end with .da, including process definitions and method main and any other Python classes and methods, okay? And inside the main, you do the configuration and you create the process and set up and start them. That's the complete thing. So here is the code you've seen. Let's look one more time. Okay, polling.da. So class P is a process class, is a process. It has a set of method. Okay, take this parameter, set responders. Pass means skip, doing nothing in Python. And this will go automatically taking every variable as sort of called a process variable. Okay, and the run method calls logic or clock, really getting the logical time. And you send a question, okay, you call any Python normal functions to the responders, to the set. You can send to single process or set of process, the same syntax. And you can wait for each R in the set of responders. You have received some received reply tuple, okay, from that responder, okay? So does underscore really match anything? I don't care what you replied, so long you send me reply, but you have to match the same T. So I identify this is a reply, okay? And I need to check that for each R in RS. And this is the R, okay? The underscore means equals that one, okay? And after you receive reply from all responders, you can output, oh, I received yes from, find the set of guys who replied yes. So you can see this is the same syntax, except here I do care, I have to match Y now, okay? So the set of R's that received the Y, again, match the same T, okay? So, so that's it, set of R, I received this from that R, okay? And I send outcome, and this outcome is again the normal Python function to the all responders. Okay, this just return a count of all the R's that you receive yes, okay, for the same T. All right, so that's the polar process. And the poly processes, each does this. You just wait to receive the outcome, anything that matches outcome, okay? And this is the sum, okay, matches the outcome, and bind this O to a variable. So afterwards you can say, oh, I received outcome O, okay? And while waiting, right, that's the yield point, and you can check if you received a message that's called question, okay, with some time from some process, and you send a reply, and here's the reply content I made up here, right, and with the same T, send back to the guy received from, okay, and here just random, import random, and return random choice between yes and no. Okay, and the main process just configure clock to be lamp ports and channel to be reliable. And you create a set of responders first, create 10 of them, needs nothing to set up, and create the polar process. And you have to pass in the set of responders. That's why I create that first. And then you start responders and you start the polar process. Okay, so that's all about the language, the Algo language, and the precise complete code on this polling example. Okay, we'll take a break, and afterwards we'll talk about the next two parts, including a demo, but the key is the setup of the framework for checking safety and liveness properties. Okay, you can ask questions anytime during the break too. Okay, thank you, see you soon.